Welcome. Today we're going to talk about orthogonal bases. This will be the first of several lectures on this topic. So suppose we have a basis of a vector space v1 through vn. There's a special property that that basis might satisfy called being orthogonal. And it's exactly what you think. It's that the vi's are all orthogonal to each other. Or another way to say that is they're perpendicular to each other. All of the vi's make right angles with the other ones. You say vi is perpendicular to vj, or if you want to write it in terms of the dot product, you just say vi dot vj is equal to 0, as long as, of course, I is not equal to j. Now we're only going to be talking about the dot product here, but the same thing applies to any inner product, but I'm just going to use the dot product for this. And the picture is simply that you have v1 and v2, for example, are at right angles, and then v3 is at right angles to that. And, well, it gets harder to draw in 4 dimensions, but you get the idea. Now, another condition is the vectors could be orthonormal, which is an additional condition. So orthonormal means, first of all, that they're orthogonal, and second of all, that all of the vectors have length 1. So that's a so-called normal condition. You say a vector is normal if it has length 1, and orthonormal is meant to include orthogonal plus the normal condition. Okay, well, let's write down an example. The standard basis in Rn is orthonormal. So let's see, what does that mean? So the standard basis, for example, if n is equal to 4, let's write it down. The standard basis is v1 is this vector, and v2 is 0, 1, 0, 0, and v3 is 0, 0, 1, 0, and v4 is 0, 0, 0, 1. And clearly, if you take the inner product of any two of these, you get 0, as long as I is not equal to j. And if you take vi dotted with itself, you get 1, which is to say the length of each of these vectors is 1. So the notion of orthonormal is meant as a generalization of the standard basis, and in important special cases, the standard basis. Now notice that we can write the condition as vi dot vj is 0 if I is not equal to j, and 1 if I is equal to j. That's just another way of writing the two conditions for being orthonormal. Now, here's what about an example of a basis which is orthogonal but not orthonormal? Well, just take something like the standard basis, except slightly different. So if the first vector was scaled to be 2, 0, 0 instead of 1, 0, 0, these vectors are still clearly orthogonal, but this one doesn't have length 1. So this is an orthogonal but not orthonormal basis. Well, let's see. What about some other examples? Are there any other examples? Are there lots of examples? Are they rare? How many are there? So the question is, are there a lot of orthogonal or orthonormal bases? Or what? So let's see, let's look in R2. Let's see if we can think about how many orthogonal bases there are of R2. Well, how do you find a basis of R2? Well, let's pick any single vector, let's say 2, 1. And now, to find an orthogonal basis, you just have to take the orthogonal complement, the line perpendicular to that, and take any vector along that line. So, for example, you can take the vector minus 1, 2. And that's clearly an orthogonal basis. These two vectors are a basis, and they're at a right angle. So it's very easy to construct orthogonal bases. You just take any, in R2, you just take any two vectors which are orthogonal to each other, and there's lots of those. Now, this isn't orthonormal, because the length of this vector v1 is what? Well, let's see, v1 dot v1 the length of V1 is the square root of 5. And the length of V2 is also the square root of 5. Well, I can make this basis orthonormal. I can modify it by scaling each vector appropriately to get two unit vectors, W1 and W2. And specifically, you just take W1 to be 1 over radical 5 times V1, 1 over the length of V1 times V1, and similarly V2. And now these vectors are still clearly orthogonal. They're still at right angles. But I've scaled them appropriately so that W1 and W2 both have length 1. And you see here the length of W1 I just computed to be 1, and the length of W2 is also 1. And they're still orthogonal to each other. Okay, so I have now constructed an orthonormal basis, starting with an orthogonal basis just by modifying each vector by the appropriate scalar. So that's something you can do in general. If you have any orthogonal basis, you can convert it into an orthonormal basis very easily. So if you have an orthogonal basis given by n vectors v1 through vn, what you do is to get an orthonormal basis, you let W1 be V1 over the length of V1, and so on up to Vn. You multiply each vector by 1 over its length. And the resulting basis is now orthonormal. So let's just check that. So for example, if you take Wi dot Wj, what do you get? Well, you get 1 over the length of Vi dot 1 over the length of Vj times Vj. And these scalars pull out of the dot product. So you can combine them to get 1 over the length of Vi times the length of Vj times Vi dot Vj. And as long as I is not equal to j, this is 0. The scalars, these lengths that you've multiplied by, don't really do anything. That's clear. On the other hand, if you take the length of the ith vector Wi, well, let's square it. That's easier. And then you get Wi dot Wi, which is, it's very similar calculation. You get 1 over the length of Vi times itself dot 1 over the length of Vi times Vi. And again, you combine the scalars to get 1 over the length of Vi squared. And now you get Vi dot Vi. And Vi dot Vi is the length of Vi squared. And so they cancel and you get 1. So that's exactly the right scalar to have divided by to make Wi have length 1. This process is called normalization. It takes an orthogonal basis to an orthonormal basis. And in a lot of ways, an orthogonal basis is almost as good as an orthonormal basis. Okay, let's just write down sort of a random example of an orthonormal basis just to get an idea. So let's start with an orthogonal basis. Let's say 1, 1, 1, 1 minus 1, 0. Those vectors are orthogonal to each other. And the third one is 1, 1 minus 2. You can check easily that all three of these vectors are pairwise orthogonal. And this is an orthogonal basis. And the associated normalization is you just divide each of these vectors by its length. And the lengths are square root of 3 and square root of 2 and square root of 6 respectively. And so this, the W's, is an orthonormal basis. Okay. So how do you find examples like this? Construct examples of orthogonal or orthonormal bases. Well, that's the Graham-Schmidt algorithm, and I'm going to talk about that next time. So just put that away for the moment. And I'm just going to conclude this lecture by an explanation about what it is that's good about orthogonal and orthonormal bases. Why do we care about them anyway? Well, they're particularly nice. And I'll show you the main thing that they're good for. And it's answering the following question. Suppose you have a basis of a vector space v1 through vn and random vector w. And since v1 is through vn is a basis, you know that you can write w as a linear combination of the vi's. And how do you find those coefficients, a1 through an? Well, we've seen how you do this. This is a matrix equation. It says that w is in the column space of this matrix A, and you're trying to find vector a1 through an, which satisfies this equation. So you put the v's as the columns of this matrix A, and you try and solve this equation. A times the vector of a's is equal to w, and, well, there's some work there. You have to do row echelon form, whatever. It's not easy. But suppose that v1 through vn was an orthonormal basis, then it's very easy. And the answer is there's a simple formula for AI, which is simply you take the dot product of vi with your given vector w. So that's wonderful. You don't have to do any matrix calculation at all. You simply take the dot product of vi with w to find the ith coefficient. So let's look at an example of that. Let's take this basis that I had earlier from a couple of slides ago, and suppose w is 1, 0, 0. Well, you just compute. w dot v1 is 1 over radical 3, and w dot v2 is 1 over radical 2, and w dot v3 is 1 over radical 6. And so what I'm claiming is that that magically tells you if you want to write w, this vector 1, 0, 0, as a linear combination, the first coefficient is 1 over radical 3, and that's times v1, which is this vector, plus 1 over radical 2 times this vector, plus 1 over radical 6 times this vector. And if you work out the constants, well, let's see, this gives you a 1/3 times 1, 1, 1, plus a 1/2 times 1 minus 1, 0, plus 1/6 times 1, 1 minus 2. And let's see, let's just check if this is really right. So let's see, you get a 1/3 plus a 1/2 plus a 1/6, and a 1/3 minus a 1/2 plus a 1/6, and a 1/3 minus 2/6. And if you work that out, you get 1, let's see, 0, and 0. Okay, well, let's see why that works that way. So you have an orthonormal basis v1 through vn, and we have any vector w. We know we can write it as some linear combination of the vi's, because that's a basis, and we'd like to find out what the ai's are. Well, let's pretend that we found them already. If you had, then you could take w dot vi and gotten that as a1 v1 plus ai vi plus dot 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 an vn. This vector, that's w, dotted with vi. And by the properties of the dot product, this is a1 v1 dot vi plus ai vi dot vi plus, and so on, an vn dot vi. And all of those dot products are 0 except for the ith. And vi dot vi is equal to 1. So this comes out to a1. So there you have it. it's this is a formula for AI. It's just w dot vi, which is what I said. Now, what if the basis was orthogonal but not orthonormal? Is there something you can do there? Well, the only difference is this number here. Instead of being 1, it's just what it is, vi dot vi. And that is to say the length of vi squared. So in that case, all you get is w dot vi is equal to ai vi dot vi. And you just solve this equation for AI and conclude that AI is, let's see, you bring this thing to the other side, is w dot vi over vi dot vi. And you know vi dot vi because you're given the basis. That's whatever it is. And so you can give this formula for AI. And if you prefer, you can write this as w dot vi over the length of vi squared, and the denominator is 1 if the basis was orthonormal.